In this video, we're going to look at L'Hopital's rule and discuss how it helps us solve limits in calculus. You might see it spelled like this with an S in here, but most people pronounce it L'Hopital's without the S. And some sources, history sources, say that it was actually Bernoulli who did the math work. I think it was Johann Bernoulli, part of the brilliant family of mathematicians, but L'Hopital was the one that published it, so he's given credit. But the historical aspects of this are not our concern today. Rather, we're going to talk about how to use it. And folks, this is it in a nutshell. So what this shows is if you're taking a limit and you have a function in the numerator and the denominator, and you end up with 0 over 0 or infinity over infinity, then you could simply take the derivative of the numerator and the derivative of the denominator and then reattempt to insert a wherever you see x. Now, of note, this is lacking a little bit of information because infinity over infinity could be plus infinity over minus infinity, minus over minus, plus over plus, any permutation of infinity over infinity. So often you'll see textbooks write it like this: plus or minus infinity over plus or minus infinity. So why is this important? Well, because it's much easier to take the numerator and take the derivative, take the denominator and take the derivative, as opposed to doing the quotient rule. So that's the benefit of L'Hopital's rule. Now, in addition to doing limits and getting 0 over 0, which is indeterminate, and then using L'Hopital's, or the same with infinity over infinity, when you initially try to plug in values for a limit, you might get something like this: infinity times 0. Or you might get infinity minus infinity, or infinity to the 0 power. All of these are indeterminate, but as is, are not amenable to using L'Hopital's rule. They are not L'Hopital's rule friendly. So the idea here, folks, is to take, if you're given initially a limit that with one of these two formats, and again, there should be a plus minus infinity and a plus minus infinity here. If you're lucky enough to get it in this format initially, you go right to L'Hopital's rule. However, if you get one of these forms, the idea is to massage these to use algebraic manipulation until you get one of these forms, in which case you proceed with L'Hopital's rule. Let's now look at our first example, which has the limit of sine of x over x as x approaches 0. So let's look at the numerator first. Recall from our unit circle that the sine of x is going to be the y-coordinate of the unit circle, depending on where we are. So if we're at x equals 0, we're talking about the input angle of the sine. So we would be 0 degrees right at this location. So this location features this point, which is 1 comma 0. The sine of that angle is going to be the y-coordinate. Therefore, the sine of 0 degrees is 0. For the denominator, it's a little simpler. We just plug x in, 0 in for x, and we get 0 over 0. And indeed, that is one of the forms that is amenable to using L'Hopital's rule. This is L'Hopital's friendly. So we're going to go right ahead and take the derivative of this and the derivative of that. We are not going to do the quotient rule. We're going to carry this expression, the limit as x goes to 0. We keep this until there's no x present. So when we take the derivative of sine of x, we're going to get cosine of x in the numerator, and the chain rule, the derivative of that x is just 1. And on the bottom, the derivative of x is 1. Now at this point, folks, we reassess and we ask ourselves, can we now plug in 0? And yes, we can. Recall, as we just had a moment ago, on the unit circle at 0 degrees, that point is 1, 0. The x coordinate of that point is the cosine. So we're going to have 1 over 1 for a final value of 1. In this next limit, we have the limit as x goes to 1 of sine of pi x over ln of x. And we are first going to attempt to insert that 1 for x. That gives us sine of pi and natural log of 1. So let's look quickly at sine of pi and invoke the unit circle. Pi puts us at this location. That's pi radians, and the coordinates of that point are -1, 0. The sign is going to be the y coordinate, or 0. To look at this natural log of 1, it's a really good idea to memorize this graph if you haven't. This is y equals ln of x, looks something like this, and it crosses the x-axis when x equals 1, and at that value the y is 0. So the ln of 1 is 0. If you, for some reason, can't remember the graph, the way to do that, the way to evaluate this limit is as follows. If you're trying to evaluate the natural log of 1, so we don't know what that value is, recall that the base of the natural log is e, so you can do what I call whirly-bird, and then set e to the question mark equals 1, and that question mark is none other than 0. So folks, we now have a 0 over 0, which is amenable to L'Hopital's. So we're going to go back to the original function, and we're going to take the derivative of the numerator and the denominator. We're going to continue to use this terminology with the limit because there's still an x involved. Okay, to do the derivative of the numerator, again, we are not doing the quotient rule. The derivative of sine of pi x is going to be cosine pi x. And then we're going to do the derivative of the inside, which is just going to be pi. And remember, you can't multiply the pi with what's inside the parentheses. So it might be more clear if you place the pi out front as a factor to cosine of pi of x. Okay, in the denominator, we're going to get the ln of x. And recall the natural log of x is, the natural log of u is going to be 1 over u times u prime times the natural log of the base of that log. And the way I think of it is, this is the argument of the log. And when you argue with your parents, you get sent right to the basement. Then we have u prime, and then the natural log of e is 1. So this all becomes, in this particular case, we're going to send this argument right to the basement. So we're going to have 1 over x, and then we're going to do the derivative of u, which in this case is the derivative of x, which is just 1. So we have now the cosine of pi times cosine of pi of x over 1 over x. So now let's go ahead and try to insert 1 wherever we see x. When we do that, we're going to get pi times the cosine of pi over 1 over 1. The cosine of pi is going to be right here in that location. That point is -1, 0. So the cosine of pi is -1. So now, folks, we're going to have no limit terminology because we don't have an x anymore. So now we're going to have pi times -1 over 1, and your final answer for this limit is negative pi. In this next limit, we have the x going to infinity of a rational function of polynomials. And recall from our pre-calculus days that when you are looking at x going to infinity or negative infinity, we're talking about horizontal asymptotes. We're talking about end behavior of this rational function. So the rules for determining where the horizontal asymptote depend on the degree of the numerator and the denominator. You may recall that if you have x over x cubed, this is a bottom-heavy function, which means the horizontal asymptote would be at y equals 0. If it's a top-heavy function, there is no horizontal asymptote. And if it is top-heavy by 1 degree, so if, for example, you have x cubed over x squared, while there'll be no horizontal asymptote, there'll be an oblique asymptote because it's top-heavy by just 1 degree. Finally, we have the current scenario where the degree of the numerator matches that of the denominator, and in that case, it's the leading coefficient ratio. So here, our horizontal asymptote is going to be 3 over 5, and if our horizontal asymptote is 3/5 right here, then this function, as x approaches infinity, is going to approach 3 over 5. Now, just looking at it, we don't know if it's going to be from above or below, but we do know that the final answer of this limit is going to be 3 over 5. But this is not a pre-calculus video, so let's talk about a couple of other ways to do this. Folks, whenever you are presented with a rational function and you're going to infinity or negative infinity, one move that you can use is to divide everything by the highest degree located in the denominator. So if we have this, and I created some space up above, we can come along and divide everything by x squared. That's the highest degree in the denominator. Now, whenever you have a bottom-heavy function, if you look at these individually, and you set that denominator equal to infinity, this x squared is going to dominate the x. It's going to get very, very big on in the denominator. When you have a very, very big number in the denominator, that goes to 0. Again, big number in the denominator, the fraction itself goes to 0. So all these bottom-heavy terms will go to 0, and we're left with what we have here on the left side of the numerator and the denominator. Here, the x squareds cancel out, and we get 3/5, which is what we predicted initially with our horizontal asymptote analysis. Okay, finally, let's get to why you came to this video. And if you plug in infinity into this equation, you're going to get infinity over infinity, which is L'Hopital's amenable. So what we're going to do is we're going to repeat the limit terminology here. We're going to take the derivative of the numerator and the denominator, not the quotient rule. That's going to give us 6x plus 2, and it's going to give us 10x minus 1. Plugging in to infinity into this fraction here, we're still going to get infinity over infinity. But folks, that is still L'Hopital's friendly, and we can continue that process of using L'Hopital. So we're going to do it again. The derivative of 6x plus 2 is 6, and the derivative of the denominator is 10. This, folks, reduces to 3 over 5, so we got the same answer for this limit using 3 different techniques. In our next limit, we see x going to 0 from the right. of natural log of x divided by cotangent of x. So let's go ahead and try to plug in 0 coming from the right. Let's do the numerator first. This is the graph of y equals ln of x. As we approach 0 from the right side, our graph is heading towards negative infinity. Now, let's look at the cotangent function. The cotangent function, unlike sine and cosine, has a period of pi over 2. A period of pi, and it's off-centered, and it's a decreasing function. So the cotangent function looks something like this. So therefore, as you approach 0 from the right side, the cotangent is approaching infinity. So we have negative infinity over infinity, and that is L'Hopital's friendly. Now, in case you didn't have that in your pocket, the graph of the cotangent of x, let's look at our unit circle and see how we could have solved that. Now remember, when you're looking at approaching 0 from the right, and you're graphing the cotangent function, you're going to have 0, and then you're going to have pi over 2, you're going to have pi. So as you're approaching 0, you're starting at pi over 2. If you're approaching 0 from the right, you're starting at pi over 2, and you're heading towards 0. So when we analyze this using the unit circle, we're going to start at pi over 2, and we're going to head this way towards 0. The coordinates of 0 degrees on the unit circle are 1, 0. Recall that the sine, is y over x. Let me start again. The tangent is y over x, which would give us 0 over 1. However, the cotangent is the reciprocal of that. So we're going to have 1 over 0. And when we do that, you could see that this y value is going to be a little bit positive. So we're going to have a very, very small positive number in the denominator. So let's see what that looks like. A very, very, very small positive number in the denominator would be 1/1,000,000th. Okay, if you had 1/1,000,000th of a piece of pizza, it would be tiny. Now, in order to simplify this, we could go ahead and multiply top and bottom by 1,000,000. I know that's not 1,000,000, but you get my point. And when we multiply the top by 1,000,000, this is going to be a big, big number. It's going to be positive. Therefore, you're going to get positive infinity. Let's get back to our limit. This is L'Hopital's friendly. So we now are going to take the derivative of the top and bottom. We are not going to use the quotient rule. The derivative of natural log of x is 1 over x. That's all in the numerator. The derivative of cotangent of x is negative cosecant squared x. We're going to take, forgot to write my limit. Okay, we're going to go ahead and simplify this a little bit. So we're going to have 1 over x divided by negative cosecant squared x over 1. Now, cosecant squared x is the inverse of sine squared x. So we can replace this here with negative 1 over sine squared x. All right, so rather than have this cosecant here, we can have 1 over x, which is the numerator, divided by the denominator, which is negative 1 over sine squared x. We're going to use keep change flip, and we're going to have sine squared x over 1. So our new limit is going to be the limit as x approaches 0 of sine squared x. I'm going to write it as sine of x squared over x. If we plug in 0 into this new simplified limit, we still get something that's indeterminate. But this time, the sine of 0 is 0, 0 squared is 0, we end up with 0 over 0. So although we don't have an answer to our limit that's acceptable, we still have something that is L'Hopital's friendly. So let me go ahead and make some room, and then we're going to now reapply L'Hopital's rule for a second time. We're going to take the derivative of the top and the derivative of the bottom. We are not going to use the quotient rule. Here's x going to 0 from the right. We're going to use the exponent rule, the power rule, excuse me. So we're going to get 2 times sine of x. Then we're going to use the chain rule and take the derivative of the inside and get cosine of x, and the derivative of x on the bottom is just 1. Now, folks, when we apply 0 into the limit, we're going to get 2 times the sine of 0, which is 0, times the cosine of 0, which is 1, over 1. So 2 times 0 times 1 is 0. This is the solution to this limit. In our next limit, we have x approaching 0 of this product, x squared times ln of x. So if we try to plug in 0 directly, we're going to get 0 times the natural log of 0, which recall is negative infinity. Remember, the natural log function looks like this. There's only one way to approach 0, and that's from the right. And as we do so, the graph goes towards negative infinity. So while this is an indeterminate form, this is not L'Hopital's friendly. Recall, the L'Hopital friendly forms of the indeterminate limit are as follows. They are both fractions. So the idea, folks, is to take this product, something times something, and turn it into something divided by something, hoping that when you plug in 0, you have a L'Hopital amenable form of indeterminate. So what we're going to do is we're going to take one of these factors and throw that into the denominator as a reciprocal. We could have done it the other way. We could have kept x squared in the numerator and put 1 over ln of x in the denominator. However, I'm anticipating that this is going to work out, and if I can take the derivative of ln of x, that's easier than taking the derivative of 1 over ln of x. So let's go ahead and use the original form that I created, this original new expression. These are the same expressions, just written now as a quotient rather than a product. So let's go ahead and plug in 0. Ln of x of 0 is still going to be negative infinity. Now let's look at what happens when we plug in 0 here. So let's do a little separate problem here for the denominator. So we're going to have 1 over x squared. Now as x approaches 0, it's going to be a really, really tiny number. So what's a really, really tiny number? 1/millionth. Okay, if you have 1/millionth of a pizza pie, it's going to be a tiny, tiny little piece. Now, as we simplify this denominator and multiply top and bottom by 1,000,000, we're going to get a big number. So this denominator is going to be a big positive number. And we're going to have negative infinity over infinity, and that is indeed L'Hopital's friendly. Now, we are now going to take the derivative of the numerator and the denominator. We are not going to use the quotient rule. When I originally created the new expression in white, I left it as a fraction because I find it easier to get the intuition of a limit when I'm dealing with a fraction. However, to take the derivative, I'm going to change the denominator into a negative exponent of -2. So all I did is I took the original denominator, I took the x squared, I moved it up top and changed the sign of the exponent. Now this is now a little bit easier to take the derivative. The derivative of the numerator is 1 over x. The derivative of the denominator is going to be -2x to the -3. I'm going to change the numerator to x to the -1 and the denominator to -2x to the -3. Now, I'm going to shift this x to the -3 up top, and that becomes x to the +3, and we're going to leave x to the -1 up top, and on the bottom we're still going to have -2. This is going to leave us with, when you multiply and the exponents have, when you multiply and the bases are the same, we keep the base and we add the exponents. So this is going to be our new form of the limit. Now, when we go ahead and plug in 0 into this new format, which we are allowed to do, okay, I should have been carrying the limit all the way with us because x is still present. When we plug in 0 into this, we now get 0. Folks, this is your final answer. In our next limit, we have the limit as x approaches 0 from the right of 1 over x squared minus 1 over sine of x, excuse me. So we're going to go ahead and try to plug in 0. This 1 over x squared, 1 over a teeny tiny number, becomes a big number. And again, the sine of x is 0, so 1 over a teeny tiny number here becomes overall a big number. So we have infinity minus infinity. This is indeterminate, but it is not L'Hopital's friendly. Recall, L'Hopital friendly indeterminate forms are both fractions. So when we're given a problem like this, we have to turn this into a single fraction, hoping that we're going to get something L'Hopital amenable. So folks, we're going to have to combine these two fractions into one fraction. How do we do that? We're going to try to get a common denominator, and our common denominator is going to be the two original denominators multiplied by one another. So this is going to be our final common denominator in our answer. So for the first one, which has x squared in the denominator, how do we get sine of x in the denominator? Well, we multiply 1 over x squared by 1, but the version of 1 is sine x over sine of x. Then, for the next term, how do we get x squared sine x in the denominator? We take the original 1 over sine of x and multiply it by 1 in the form of x squared over x squared. So now all we need to do is simplify these numerators. So in our numerator, we're going to have sine of x minus x squared all over x squared times sine of x. Now we're going to hope that when we plug in our limit as x approaches to 0, that we're going to get a L'Hopital friendly form of an indeterminate limit. Sine of 0 is 0, minus x squared is 0, over 0 times 0, and indeed this is L'Hopital's friendly. So let's now regroup. We have a brand new limit to work with that we are allowed to use L'Hopital's. We're going to take the derivative of the numerator, the derivative of the denominator. We are not going to use the quotient rule. Okay, let's do the derivative of the numerator. The derivative of sine of x is cosine of x minus 2x, which is the derivative of x squared. Down below, to do that derivative, we do need to do the product rule. So we're going to do left d right, so x squared times cosine of x plus right d left. Okay, now we're going to try to plug in 0. When we plug in 0, cosine of 0 is 1, minus 0, so we have 1 in the numerator. On the bottom, we're going to have 0 times 1, which is 0, plus the sine of 0 is 0 times 0. We're going to have 1 over 0, and 1 over a very, very, very small number is going to be infinity. In our next limit, we have the limit as x goes to infinity of this exponential function. Folks, whenever you see this, an exponent in the, an x in the exponent, and x is your base, we're going to have to use logarithmic approach to help us get this into L'Hopital amenable format. Originally, we could try plugging in infinity, and we're going to have infinity to the 1 over infinity power. Whenever you have 1 over a huge number in the denominator, this entire function that entire fraction goes to 0. So we have infinity to the 0 power, which is indeterminate but not L'Hopital's friendly. So this is what we do, folks. We let y equal x to the 1 over x. Then we take the natural log of both sides. Then we use the power rule of logs and bring this out front. Natural log of y equals 1 over x ln of x. Now we're going to take the limit as x approaches infinity of both sides. Okay, so we're going to do the limit as x approaches infinity here, and the limit as x approaches infinity here. Now, we're only going to focus on this limit. We're going to leave this left part alone. When we get our final answer, here on this limit, we're going to get a result. We're going to take that result, whatever it is, and we're going to put it in a little tiny box. Okay, so here's our result. We're going to put it in this little tiny box. And then to get our final answer, we're going to exponentiate it. And we're going to take this box and take e to whatever power that is. That is the game plan. That's because we want the limit of y, not the limit of the natural log of y. So exponentiating it at the very end undoes that natural log. You'll see what I mean in a minute. Okay, so let's now focus on what's in this orange rectangle. We're going to forget about that and remember to exponentiate at the very end. Okay, so now if we plug in infinity into this x, we're going to have, first of all, I'm going to make this a fraction, which is a good start when you're trying to work with L'Hopital's. The natural log of infinity, recall, here's our natural log function. As x approaches infinity, the y value of the ln of x heads towards infinity, And if we put infinity in the denominator, indeed we have a L'Hopital-friendly indeterminate form, which is infinity over infinity. So folks, we're going to go ahead and we're going to take the derivative of the ln of x over x. Let me rephrase that. We're going to apply L'Hopital's rule to this limit that you see here. We are not going to use the quotient rule. All right, so this is going to be the limit as x approaches infinity. The derivative of ln of x is 1 over x. That is in our numerator. And the derivative of x is 1. Therefore, we're going to have the limit as x approaches infinity of 1 over x. When we plug infinity into that denominator, our limit is going to be 0. So we're going to have our limit is equal to 0. That is the result. We're going to take that result and we're going to put it right there as an exponent of e. E to the 0 power is 1. And folks, that is our final answer to this original problem, 1. Very quickly, folks, just going back a few steps, the intuition here, the limit as x approaches infinity of 1 over x. This is a bottom-heavy function, and a bottom-heavy function as x goes towards infinity is going to have a horizontal asymptote of 0. And recall the graph of 1 over x looks like this. So as x heads towards infinity, this graph goes to 0. But again, we take that final limit, limit result, we put it in a little box, and we put it into the exponent of e. This, at the risk of being repetitive, is our final answer. In our next and final example, we have the limit as x approaches infinity of e to the x plus 10x quantity raised to the 1 over x power. So let's go ahead and plug in e to the x, the graph of e to the x. It's a growth function that goes like this, moves away from the horizontal asymptote as all growth functions do. So that's going to be infinity, and 10x is infinity. And then 1 over x, 1 over a very, very large number, is going to be 0. So basically we have infinity raised to the 0 power, indeterminate but not L'Hopital's friendly. When we see an exponential function and we're trying to get L'Hopital's involved, we're going to use natural logs. We're going to set y equal to what's on the right side here of the limit. Then we're going to take the natural log of both sides, and we're going to forget about the natural log of y to the very end. All right, so eventually, if we rewrite our limit format, we're going to have natural log of e to the x plus 10x raised to the 1x power. We're going to forget this guy. At the very end, whatever our result is from this limit right here, whatever we get, we're going to put that in a little box, and at the very end, we're going to put that as an exponent to e, and that's going to be our final answer. Okay, let's go through the progress of this. I'm going to take this away, and immediately we're going to invoke the power rule of logs, which means we're going to bring this over here. So now we're going to have 1 over x times the natural log of e to the x plus 10x as x goes to infinity. As x goes to infinity, this is going to become infinity, that's going to become infinity. This new version of the limit is going to be infinity over infinity, and this is L'Hopital's friendly. So let's go ahead and take this limit using L'Hopital's, and we're going to take the derivative of the top and the bottom. Okay, the derivative of the top, we're going to put this in the denominator. Okay, so we're working in the numerator. I'm going to give myself plenty of room. So the derivative of ln e to the x plus 10x is going to be 1 over the argument and then using the chain rule, we're going to take the derivative of what's inside, which is going to be e to the x plus 10. The derivative of the numerator is going to be 1, so basically we're just left, the derivative of the denominator, the derivative of x is just 1, so in essence we're just going to be left with the derivative of the numerator. So let's go ahead and create our new limit. Alright, we're still going to invoke the limit as x goes to infinity because we still have x in our expression. Now, if we plug in infinity here, we're going to have infinity over infinity. This is still L'Hopital's friendly. Now, at this point, if you want, you could say to yourself that the 10x and the 10 are going to be insignificant, and we really have e to the x over e to the x. But if you're not quite convinced, let's take the derivative of the numerator, which is e to the x, the derivative of the denominator, which is e to the x plus 10, and I think we'll all agree that that 10 is insignificant. You have e to the x over e to the x, which is 1. Folks, that is not our final answer. We're going to take this result, put it in a little box right there, and we're going to exponentiate with that answer right in there. So that's going to be e to the first or e. Folks, this is the answer to this limit.